Lesson 7 is transformations and symmetry, and 7.1 starts off with reflectional symmetry. And starting up at the top, I'm going to read those first few lines as is, and then I'll kind of dissect them a little bit more. So, a figure has symmetry if certain rigid transformations cause the image to coincide with the pre-image, which means to map the figure back onto itself. So remember that rigid transformations are something that maybe move or like reflect the original figure without actually changing like the shape or the size of it. And coincide just basically means that they would like overlap exactly. So like if I had a like circle and I reflected it over itself, it would land back exactly where it was before, so it coincides. The image would coincide with the pre-image. And then in the next section, if a figure has line symmetry, it can be reflected over a line so that the image coincides with the pre-image. So like a circle, for example, has line symmetry, it could reflect over a line that goes down the middle of it. And when it reflects over that line, it would coincide or it would land exactly where it was originally. And then the third section, a line that passes through the figure is called the line of symmetry. So whatever line we reflect over is called the line of symmetry. And then some figures have more than one line of symmetry. So it is possible to have more than one. So over here, this is an example of when, or a figure that just has one line of symmetry. So if I kind of pop this line down the middle, if I reflect over that line, the figure would land exactly where it was originally. And then over here, we have an example of one that has two lines of symmetry. So like with this rectangle, I can reflect, I guess, like horizontally, and it would land exactly how it was before, or I can reflect it vertically and it would land exactly as it was before as well. Okay, the next section. So for any regular polygon, and a regular polygon is a polygon where all the sides are the same length and all the angles are the same measurement, the number of lines of symmetry is equal to the number of its sides. So we have a couple different regular polygons here. This is has 1, 2, 3, 4, 5 sides, so it's a pentagon. And that means that it would have 5 lines of symmetry. There's one right here, there's one right here, right here, right here, and then right here. So if you look at all of them, they're basically like going from each point and then they go like straight across to the opposite side and it cuts through like the middle of the side that's opposite of the point. And then for the next one, we have, it looks like a hexagon. We got 6 sides. And so that means it's gonna be 6 lines of symmetry. So on these ones, though, they look a little bit different. They go from point to point, just because we have like an even amount of points, as opposed to like Pentagon had 5 points, this has 6. And then moving on to 7.2. So actually, let me backtrack. So this was, like I said, this was reflectional symmetry. So like when something is reflecting over a line or reflecting over itself, we call it reflectional symmetry. 7.2 is rotational symmetry. So rotational symmetry occurs when a figure can be rotated more than 0 degrees but less than 360 and the image coincides with the pre-image. So the like more than 100 and less than 360 just basically means it is rotated, but it's not like a full rotation to where it like lands back on itself automatically, because that would happen for any figure. So it's some rotation between 0 and 360 where it lands back on itself. The image and the pre-image coincide. So the point about which the pre-image is rotated is called the center of symmetry. So like for reflection, it was a line of reflection, and this is something we're rotating around, so it's a center of symmetry. And then the next section, the angle by which the figure can be rotated to align with itself, is called the angle of rotational symmetry. So a bunch of vocab here. I would just kind of like maybe accumulate a list for this section so you could refer back to it. And then on the right side, this parallelogram does not have line symmetry, and I'll show, or sorry, I'll try to draw like a few different symmetry lines to prove that, but it will have rotational symmetry. So like, if I draw a line through the middle here and I reflect it, it's not going to be the same exact figure, because like this side is, the long side is gonna like flip over here, and it'll end up just being like the opposite. So it would be like this if I reflected it over that line. If I did a, oops, sorry, if I did, I'm trying to erase, sorry. If I did like a horizontal line of reflection and I flipped it over that line, then it would look something like this. So there's actually like no line that we can reflect over, even like a diagonal. It just doesn't work with a parallelogram, at least this one. But it does have rotational symmetry. So if I take this and I just rotate it like 180 degrees, and it could be clockwise or counterclockwise, it's going to land at the exact same spot. So if I just basically were to spin this object around this point, this tip would like end up over here, this would end up down here, and it would land exactly in like the same footprint as it did before. So like I said, we can rotate it 180 degrees and it could be clockwise or counterclockwise because if we're going 180, that's like a half rotation. So it doesn't matter if we go clockwise or counterclockwise, it's going to be the same. Picture it as in like if we go halfway around a circle, it doesn't matter which direction we go, we're going to land in the same spot. And then the next section, so regular polygons again. Regular polygons have rotational symmetry as well as like they had reflectional symmetry up here. So to find the angle of rotational symmetry for a regular polygon, you have to divide 360 degrees by the number of sides of the polygon. So we have a couple of examples here. We have a square. So with a square, like I only need to rotate a square 90 degrees for it to land back exactly on what it looked like before. And we're always looking for like the smallest angle measurement that would give us that like those points that coincide. So there's obviously like an infinite amount of rotations that we can go and still land in the same spot on the square, but we want the smallest angle that'll give us that same figure. So 90 degrees, and you can always find that, like if you're not sure, you can just do 360 and then divide that by the number of sides, which there's 4 sides in a square, so 360 degrees divided by 4 is 90 degrees. And then for a pentagon, they have it drawn on the picture, but if we weren't like sure what the exact angle is, because it's kind of hard to see that if we're not given it, we can do 360 divided by the number of sides. So in this case, a pentagon has 5 sides, and 360 divided by 5 is 72 degrees. So it would take a 72-degree angle before like it rotated and it landed in the exact same footprint that it was in before. But like I said, this is only for regular polygons, and we defined regular polygons up here. They have to have the same side length and the same angle measurement in all the angles. So like a square has 4 sides that are the same and 4